Hello, mother lovers. 2011's MAT today. Let's get going. So first one, we're given some cubic. Which one is the correct one? So we can first of all see like they all need to go through at 1, apart from this one. So let's just check, does it work at 1? Well, 1 take 1 is 0, minus 1 plus 1 is 0. So x minus 1 is definitely one of the roots. So that does rule out D straight away, like we know that's not the correct answer. What do we need to make this cubic? Well, we need to have something to make the x cubed. So that's going to be an x squared out there. These two bits together make us a minus x squared. So we don't need any x term in there with that one to make an x squared. We need to make a minus x. So this x and a minus 1 on this side. And then that makes the plus 1. So we're all good. Everything's worked out correctly. And this x squared minus 1, we can rewrite that as x plus 1, x minus 1. So it's the same as having x minus 1 squared and x plus 1. So we have a repeated root when x is 1, i.e. this bit down here. So C should be the correct answer. Next bit then, rectangle has perimeter P, area A, and they must satisfy some inequality. So we can imagine the perimeter would be 2 lots of x plus 2 lots of y. If we think about having some like x times y for our rectangle. So the area then is x times y. So we can rearrange this one and say that y is equal to a over x. And as we sub that in then to perimeter, what we get is that we're going to have 2x plus 2a over x. If we make this into like a quadratic, like it's x squared, so 2x squared minus px plus 2a, all equals 0. And we know then that this needs to have some actual values. So we should have the discriminant be positive. So the discriminant p squared minus 4 times by a, which is 2, and times by c, which is 2a. That needs to be positive. So what we have, p squared is bigger than 16a. And that is this one, well, it's bigger than or equal to. Is that all good? B for the next one. Yep, lovely jubbly. Question C then. So here we have some sequence. What's the largest value for which this is true? So this means basically the next term is smaller than this one. So it's the same as it being decreasing, yeah. This is a cubic. I know it's going to be a sequence, so it's just being integers, not all the values. But in general, a cubic is going to go up, down, then up again. So if we want to find what's the biggest value for n when it's decreasing, we're really looking for like that sort of value down there. So what I'm going to do is differentiate it. So we're going to have 3n squared minus 18n. The 631 goes away. We set that equal to 0. We can find that n is either going to be 0 or 6. So they're the turning points that we get at 0 and 6. So we want to find the value of n. So the next one is smaller. Well, all of these ones are bigger than 6. So they're all in this kind of region over here when it's increasing. The only one when it's decreasing is going to be the 5. So 5 should be the correct answer in that case. For part D then, we need to find the fraction of the interval 0 to 2 pi for which one or both of these things are true. Okay, so let's think when we have half of both and it's sine on both. So if we think about doing sine inverse of a half, what numbers do we get from that? Well, the first one is 30, which is pi on 6. And then 150, which is 5 pi on 6. And then we want to go 0 to 2 pi, but this is like 2x. So you can imagine this going basically to 4 pi. So as we go again, if we add 2 pi to all of those, it's like adding 12 onto the top effectively. So we'll have 13 pi on 6 and 17 pi on 6. That's useful. So then we have answers for both these inequalities, like pi on 6 here and 5 pi on 6. This one then will be pi on 12, 5 pi on 12, 13 pi on 12, and 17 pi on 12. And it's going to be like between those two, and between those two. All the stuff we've got on the right is over 12. So I'm going to rewrite this to be over 12 as well. So it should be 2 pi on 12 for that one, and 10 pi on 12 for this. So we can draw some number line out where we're going to have, well, we'll put a 0 on. We'll have we got 1 pi on 12? We got one of them. We have a 2. We have 5. We have 10. We have 13. We have 17. And then the end would be 24. Although it's a 2 pi. So these are all over 12. Yeah, these are not counted in pi on 12. So any between pi on, well, 2 pi on 12 and 10 pi on 12 is going to be correct. So 2 and 10. Between 1 and 5, so that one as well. And between 13 and 17. And then we don't have the other bits. So that's all good. How many bits do we have then? Well, we can think about this kind of section from there to there. That's going to be 9 altogether. This bit is 4 in that little section. So altogether that's 13 of them. 24 altogether. So we should have 13 over 24 for the answer. D, was that correct? Let's find out. D, the answer is B. Lovely. E then, this next one has a center C, all of these different angles. We want to find some relationship. Okay, so one thing that's probably useful in circles is thinking like, we can call this a radius, and we can also call that a radius. So we can start to do some bits and think like, we want to have this angle, definitely, don't we, in our relationship, do we? Yes, it's in all of them. So we need to somehow get onto this triangle and get the alpha onto there. Well, we have some right angle triangle. So what we can do, if we call this h, like hypotenuse of the triangle, we can say that we know that the opposite and the hypotenuse are linked together by cos. So we have, by alpha, sorry. So we're going to have sine of alpha is r over h. So yeah, h itself then is r over sine of alpha. So now we have something about alpha in this triangle as well. Lots of these things are to do with sines, aren't they? We have some causes, but not too many. And we think about doing the sine rule on here would be good. We don't have enough stuff for cosine rule. That would find us like this length if we knew this angle, but we don't have that information about either bits, so we can't really use that one. But the sine rule, we have this and this, and we have this and this. So let's fill that in. What are we going to have? So sine of beta over r will equal sine of gamma over h, which is this thing. So over h, we can flip it upside down. The r will go on the bottom, and the sine alpha goes on the top. Cancel those two r's off. What we're left with, sine b, well, sine beta equals sine gamma times sine alpha, which is B for the answer. Lovely jubbly, is that correct? Answer is B. Yeah, nice. What's going on down here? So we've got some circle. Okay, we're going to find out what values of theta is this circle valid. So let's complete the square. We'll complete the squares, I suppose. We'll have x plus 2 cos, all squared, plus y plus 4 sine, all squared. And if we take that equal to everything else, so the 10 will go over and be negative, but we're also going to get 4 cos squared and then 16 sine squared. If you think about like as we've made these brackets, what needs to be on the other side is the takeaway parts. And then this 10 as well will come over, so minus 10. What we can do, cos squared and sine squared make 1, don't they? So that right hand side is the same as having 12 sine squares. So stealing 4 of them there, combine it with those 4 to make just a 4. Take away the 10, we have minus 6. This is a circle, so this is the radius, well, the radius squared, yeah. So we need this thing to be positive. Notice in here, like they're not including equal to, so their definition of a circle is not one of radius 0, just by the way they've done it. It seems to be bigger than 0 in this case. So what we have is that sine squared is bigger than a half, or that sine is bigger than root 2 on 2. It would be like less than minus root 2 on 2 as well, but it's between 0 and pi, so we know it's always positive. So doing that, what do we have? Well, these give us 45 and 135, don't they? So that's pi on 4 and 3 pi on 4. And we need to be between those two. So yeah, B. F, the answer is B. They've all been B. That was B. That was B. This one was B. That was A at least. C and a C. It feels like lots of B's. That looks good though. Yep, that looks all good. On to G then. So we have some function sketching the axes. We want to find the value of putting x squared minus 1 into that function and integrating it from -1 to 1. So what is this function we have? Well, on the left-hand side, if we're between -1 and 0, what do we have is this straight line. It goes through 1, comes from -1, so gradient is 1 as well. So it's x plus 1. Similarly, it's 1 minus x on the right-hand side, and that's between 0 and 1. When we look at the x squared minus 1 then, which one we use here depends on this value. But we're looking at between -1 and 1. So the x squared minus 1 is always negative. X squared, if you're between -1 and 1, is always going to be between 0 and 1. So if we take away 1 from that, we're always going to be between -1 and 0. So we could be 0, I suppose, not necessarily negative, but it's not positive, non-positive. So we don't want to be looking at the positive side here. We want to be looking at the negative side. So effectively, f of x squared minus 1 is equal to x squared minus 1. Looking on the positive side, we add 1. So just x squared. So we're going to integrate x squared from -1 to 1. We get x cubed on 3. Evaluate that at 1 and -1. The negative, when you do the takeaway, they'll all cancel out. It's 2/3 at the end, isn't it? 2/3 there. So it's not going to be 1/3. I think some people might do stuff with like even functions and be like it's symmetrical and stuff like that, but it's not quite going to work as easy as that in this case. Was that correct, first of all? D for G. G is D. Wonderful. This one, so this is, yeah, I looked at this before, and there's a bit, one idea to think about first of all before you do anything else really is like these are all the same idea, just in different forms really. But let's deal with this thing first. So these are just numbers, so this is also just a number. What it's asking for, if we have 0.5 to the power of what is 0.25. So if I square half, I get a quarter, yeah? So this is just 2. And all of these are the same form. Let's look at this one. So we have a power, or base of 2, and it's a power of 2 as well. So I can rewrite this as 2 cubed times by, well, it's going to be like this. Log 2 cubed to the power of log base 2 of x. And then we can swap those powers around. So it's 2 to log base 2 of x cubed. And that thing inside the bracket is just x. So that is x cubed. This is going to work very similarly then if you think this is 3 squared, yeah? So this is x squared. This is 2 squared. So it's going to be x squared there as well. And that's just a 2. So this is our entire equation that we have. Let's try and rearrange this. So we have x cubed minus 2x squared minus an x and plus a 2. Often they're going to make these have 1 as the solution. Does it work? 1 minus 2, well, 1 minus 1, 2 minus 2. So yeah, x minus 1 does work. It's always one just worth checking. Do you mean, or check -1 as well if that's not going to work. What else do we need from that one? Well, to make the cube, I need a squared. I need to end up with minus 2x squareds. I have minus 1 of them there. So I need 1 more. I need to make them by plus 2. I have a minus 1, so I need a minus 2. And then we can factorize that bit as well. We'll have a x minus 2 and an x plus 1, and still the x minus 1 from here. So 3 solutions all together, but we wanted positive values. You think as well, they go inside logs, don't they? They had to be positive. So this one is good, this one is good, this one is bad. 2 altogether. H was C. H was C. Lovely. I then. So range 0 to 2 pi is normal. How many of them do we have? So let's have a look. We can take the cos to the 6 and rewrite it as 1 minus sine squared. Sorry, that's cos squared, yeah? Cubed. So equal to 1. Let's go and expand some brackets. Sine to the 8 plus, this is going to be, not plus, but minus sine to the 6 plus 3 sine to the 4 minus 3 sine squared. We'll have a plus 1, but with that plus 1, they'll cancel off. So that's all equal to 0. So we can take some sine squared out the front. We'll have sine to the 6 minus sine to the 4 plus 3 sine squared minus 3. Does this thing have 0 go 1 into it? 1 minus 1 is 0. 3 minus 3 is 0. So it does. So we've got sine squared there. Sine squared minus 1. What else do we need? We need a sine to the 4. That makes me minus 1 of them. I already have that, so that's good. So I don't need any middle term. And then I need to make a 3, well, minus 3. So I need a plus 3 on the end. So either s squared equals 0, or s, I suppose we can think about it even instead, will be 0, or plus or minus 1. Here you could have like the fourth root of 3 times by I, yeah, but we don't deal with that in this paper. So 3 solutions there for sine. How many of these actually give us, though, in our range from 0 to 2 pi? Well, for the 0, that happens at 0 and at pi. The 1 happens at pi on 2, and the minus 1 at 3 pi on 2. So 1, 2, 3, and 4. I, is that B? I is B. Lovely. Last one then, for the multiple choice parts. We've got some function defined for positive integers of n according to these rules. So start at 1. If you've done half of this before, then you're going to do that same value. And if it's a different something that you've not done before, you take the half of the value and square it, take away 2. So let's look at some of them. We know the first one. What's the second one going to be? Well, we've done half of that, haven't we? We've done 1, so it's just the same. Should be 1 as well. Let's look at 3. I haven't done half of that, so I need to look. N would be 1, so look at making like 2 times 1 is 2, plus 1 is 3. So look at 1 was 1, square it is 1, take away 2 is minus 1. When we look at 4, I've done half of that. It was 2, and that gives us a value of 1. 5 I haven't done, but we go and look at 2, which we had 1. We square that, we get 1. We take it away, we get minus 1. For 6, I've done half of that. It's 3, wasn't it? So it's going to be minus 1 again. So by the looks of things, we're only going to get 1s and minus 1s. Can we kind of confirm that for sure? Well, we start with 1s. So anything that's a multiple of 1, as in like it's a double. So 2 will just be the same one as 1, and then 4, and then 8. So all the multiples of 2 should be like this. And I'm guessing if we get 8, that's, yeah, because 8 will look at 4, won't it? And then 16 will look at 8. So they're always just looking at the one before it, and they're just going to be the same forever. With these minus 1s then, so that's whenever we look at something that's not got a 1 before it, basically. Because if we had a 1, if we've already seen the 1, it's just a 1 again. If we, however, look at something different, this always outputs 1. If we have minus 1 and 1 to start with, it always outputs minus 1. So this is just the same as writing equal to minus 1, really. So all we can do is either be equal to 1, be equal to something that's already happened in the list, or be equal to minus 1. So the list is entirely 1s and minus 1s. How do we get a 1 is if we had a 1 for half that value. So the only time that's going to happen is in the powers of 2. So I think what we have is that everything is either going to be basically f of n equals either minus 1 or 1. It's minus 1 if it's not a power of 2. And it's 1 if it is a power of 2. So how many do we need to work out? 100 of them. So we should have minus 100. But that's overcounting, so that's including all the powers of 2 as a negative. So you add on 2 times how many powers of 2 there are. We'll have 1, we'll have 2, we'll have 4, we'll have 8, we'll have 16, we'll have 32 and 64. 1, 2, 3, 4, 5, 6, 7. So that gives us minus 86, which is, oh, that's an answer, isn't it? That's good. J, A. J is A. Wonderful. That all sounds good to me. Right, question number 2 then. We're given some x cubed is 2x plus 1. We want to find what x to the 4 is. So we'll take this thing, times it by x. So 2x plus 1 all times by x should give us 2x squared plus x, which looks good to me. So that's going to be x to the 4. And now then, we want to find x to the 5 as well. So we'll take what we just found, 2x squared plus an x, and we'll times that by another x. So we'll have 2x cubed plus x squared. And you can see in the thing that we found, we don't have anything bigger than x squared. So we want to take our x cubed we have in our expression and replace it with the x cubed we were given above. So there should be 2 lots of 2x plus 1, i.e. 4x plus 2, plus the x squared. And that looks good compared to that bit. Part 2 then. We want to find, well, for every integer k that's bigger than 0, or could be 0, we can write this thing down. So we're taking some expression for x to the power of k. We can always write them as some quadratic, basically. These are all integers, blah, 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 shown in part 1. Okay, so that's what the ones we've been given above. You can see the 0, the 1, and the 2 are going in there. The 2, the 4, and the 1 are in there. So we want to show that the next terms, how do we find the next terms, basically? So if we think about the one we're given here, we can use that to find what is xk plus 1. Because it's going to be all of these bits, but just times by x. So we're going to have effectively akx plus bkx squared plus ck x cubed. And we know x cubed is 2x plus 1. So if we were to regroup everything up now, how many x squareds have we got? Just the bk of them. How many x's do we have? Well, I've got my ak up there, and I've also got 2 ck's. Lots of x. And then how many constants do I have? I have just the ck in the term at the bottom. So when we go and think about what each part of these are, we know that the single term, the constant term, should be ak. So we effectively have that, like, this bit is ak plus 1. The bit above it is going to be bk plus 1. And then above that is ck plus 1. So we've shown the top one, ck plus 1 was bk. We've shown that bk plus 1 was ak plus 2 ck. And we've shown that ak plus 1 was equal to ck. Is that all good? Is that what we wanted? ak plus 1 is ck, bk plus 1 is ak plus 2c, and c plus 1. Yep, that looks good to me. Part 3 then. Let d equal to some combination of the bits that we have. Show that the next term of d is equal to the negative of the current one. Okay, and then show this thing. Just to note, this thing is the same as the one above, just rearranged ever so slightly, and we've replaced the dk with this. So we want to show basically that dk is equal to minus 1 to the power of k. So how are we doing that? Well, we have our dk, and all we're going to do is think about kind of rewriting that in terms of dk plus 1. So if that's dk, dk plus 1 will be ak plus 1 plus ck plus 1 minus bk plus 1. And using the stuff we just found on the question before, ak plus 1 is just ck. bk plus 1, well, let's do the ck plus 1 next, is bk. And then bk plus 1 is going to be ak and 2ck, and they're both being subtracted because of the subtraction in there. That looks good. We can rearrange ever so slightly then. We've got ck there, minus 2ck there. So what we have is bk minus ak minus ck. And look up here, is exactly the negative of that stuff. So that is, if you want to make sure you get it all the marks, we can put negative of AK plus CK minus BK, and that is the same as just negative DK. Looks good. We want to then go through and find the bit with a negative 1 to the power K. How are we going to do that? It's just looking at some of the original values that we have. So if we go and look at what is the value of D0, so that's going to be the same as like the expression for x to the 0, so just a constant. Well, what is that? I don't think we had any version of that, did we? I don't think we did at all. Are we given anything anywhere about that? No, we are given that one. Are we given anything useful? No, but this is just, what am I doing? Yeah, x to the 0 is equal to 1, isn't it? So what we can see from that bit, if we go and look up, what do we have for the constant term? The constant term was a. So when we have x to the 0, i.e. when k is equal to 0, what we have is that ak is equal to 1, bk and ck are both equal to 0. So that tells us our dk is going to be equal to, adding those bits up, well, we can use the one up here, ak plus the ck minus the bk. Well, they're both 0, so they make no difference. So it's the same as ak, so it's just 1. That's actually happening not for the k, sorry, but for 0, isn't it? And then we use like this negative fact. The next one is going to be minus of that. So we have that d1 is equal to negative 1, d2 is equal to 1, etc., etc. So what does that tell us? dk is equal to minus 1 to the power k. So we can take our expression that we had up here and replace dk with minus 1 to the power k. So this thing, minus 1 to the power k, is equal to ak plus ck minus bk. So rearranging that for what we want, ak plus ck is equal to bk plus minus 1 all to the power of k. That looks good. Last little bit then, just to do the stuff with f, I will just shrink some of this out of the way, give me some more space. There we go. So f is the sum of a and c, and we want to show that as you add two of them together, you get the next term. So basically show that f is the Fibonacci sequence. So let's write it down then. We're going to have fk plus f of k plus 1. What's that going to equal? Well, the fk will be ak plus ck, and the k plus 1 will be a k plus 1 plus a c k plus 1. Do we have any expressions for these? Well, yeah, look at this. We can just replace what we know in both cases with lots of b's. So doing that, this thing is going to be bk plus minus 1 to the k, and this thing is going to be bk plus 1 plus minus 1 to the k plus 1. And I'll get rid of the plus 1 up there, so basically extracting one of those minus 1s to turn that into a minus, and then immediately those two bits can cancel out straight away. So all we're left with is bk plus bk plus 1. And from here then we're able to go through and get out using the facts we had at the very start, not the very start, but these ones in the middle. So I can transfer to the next c, yeah. So I know that bk is the same as ck plus 1. So this bit will be ck plus 2. And then I do a very similar thing. I can transfer to the next a as well. So it's ak plus 2 plus a k plus 3. I don't want that though. Let's leave the c as it was. So c k plus 2. And now everything's in k plus 2, which is good. And we want k plus 2. Everything there is k plus 2. F, we were told, yeah, it's just a plus c, isn't it? So we're done. This is f of k plus 2. And this looks good then. I think we've done every bit of it. That's k plus 2. We got that expression out over there, didn't we? No, up there, sorry. show that all the A stuff is true. Yep, that's in there. We got those bits. We can write that. And yeah, we got those bits out as well. Lovely. That all looks good to me. On to the next one then. Okay, question number 3 then. So we've got x cubed minus x, m times x minus a. They're both on this axis. M must be positive. A is less than or equal to minus 1. They meet at point A. Sorry, this meets the x-axis at point A. They meet at point B and at point C. Notice at point B it just touches. So what that tells us, it is a tangent. And they meet again at point C, and we call those the lowercase letters for the x-coordinates. Using the fact that they touch when x is b, show that this is true. So yeah, when they touch, it's a gradient. So if we think about the cubic, do the differentiation of that, what we're going to get is 3x squared minus 1. And we know then that when we plug in the value of b, that should be the same gradient as the straight line, i.e. m. So therefore, m is equal to 3b squared minus 1. For part 2, it's a very similar idea, but we want to do more bits, now not using the gradient, but just using the y-coordinates of them both. So if we plug b into there, we're going to have x cubed minus x is equal to plugging b into the straight line, m lots of x minus a. And that x, remember, all of these x's now going to be b's, because this is only true at point B and at point C as well. But we're doing it for point B. Nothing about C's yet. So this is good. We want to rearrange for A. So let's do that. We can divide by the m. So we're going to have b cubed minus b over m. That will equal to b minus a over here. We want to get a by itself, so I'm going to add the a over and subtract this bit over. So it's basically going to be b minus that stuff is equal to a. M as well, from the last question we have this. So we can replace that and make one common denominator. Times in this original b by this stuff, we get 3b cubed minus b, and then plus the other bits in the bit before, so minus b cubed and plus a b. And that's all over the m of 3b squared minus 1. And then that top row, lots of bits cancel out. We end up with just 2b cubed over the thing we had for m, the 3b squared minus 1. That all looks good. That's part 2 done. Now then, if a is minus a million, what is the approximate value of b? So we know we have to have a tangent there. A being minus a million basically sends it all over there, and it's going to you're going to go across 1 million, or 1 million minus b, and up 1. So the gradient is effectively 0, approximately 0. So the graph is just going to be a complete horizontal line. Where, roughly, do you know what I mean? So where's that going to hit this point is going to be at the turning point of the graph. So if we take the derivative of it, 3x squared minus 1, and set that equal to 0, what we end up with is that x is going to be equal to, it's going to be the square root of a third, so root 3 on 3. So therefore, b is approximately equal to that value. Should be plus or minus that root 3 on 3. We want the negative value of it. B's on the left. So that looks good to me. Yeah, all looks good. Using the fact that this is true then, which you don't need to prove, show that c is equal to minus 2b. So not much else we can do but expand things out, yeah? We could try and rearrange, but you can see there's lots of x's and m's and stuff going on. So the only way that we can actually eliminate the x from this, generally, is when we expand, and you're going to see like the coefficients of everything, and they should match out on both sides. So on the left, what do we get? We'll have an x cubed. How many x's do we have? Minus 1 and minus m. So m plus 1, but negative of both of those. Constants, we have am. Nothing here includes b or c. Everything includes something else. Well, the m's, I suppose, you can get the m's out. But we have this a, but now we do have expressions for a as well. Generally, though, it's not going to be always that complicated. It should be quite easy to see them when it spots out. Similar thing on the right-hand side, then. Let's have a look at doing this expansion first. What do we get? Well, we'll have some x squared minus 2bx plus b squared. We then want to take that and times it all by x and all by c. So think about the bits of x cubed then, will just be that bit times x. To make x squared, we're going to have this thing times x and this times c. So we'll have c minus 2b, lots of x squared. And you can actually see that's what we're going to need. That should be what pops out the other side. Sorry, it's going to be minus c. So it'll be minus on both of these, should be a plus in the middle. Yeah, that is going to be what we need. We could continue doing the expansion and get the rest of the bits out, but we don't actually need that. So all we need to do, compare the x squareds on both sides. How many on the left? None. How many on the right? C plus 2b. So we know then that c is equal to minus 2b. I'm just going to circle our kind of final answers that we have. That bit and that bit. Lovely, that's number 4 done then. Part 5 then. R is the finite region bounded by the line and okay, yeah, in between here. For what I believe A's are the largest, and then find that value of R. So value of A. So we basically it still has to go through B, doesn't it? B is going to move around depending on where A is, because you can't just move it over there and B stay the same, because it's always going to be a tangent. So how can we move A to make this area be the biggest? Well, as we move A, it's going to move C in the other direction. If I move A that way, it's going to move C down. If I move A this way, move C up. You can see if I move C down, that's going to shrink the area, because I'm just going to lose this bit of it. And vice versa as well. If I lift it up, I gain this extra area. So ideally what I want to do is get C to be as high as possible. So that means bringing A to the right as much as possible. What was the limits on A? Less than equal to -1. So we want that one. So if we have A equal to -1, what else is that going to tell us? Well, B then, it's the intersection, but intersection between those 2 points. It will be -1 as well. You can see that from looking at this. If we make this -1, you can rearrange, and B is going to be 1 as well. C then is going to be 2, and M is going to be 2. So that's everything we have. We want to find the largest value of R then. So that's the difference between the straight line, i.e. 2 lots of x plus 1, and the cubic we have, x cubed minus x. I'm integrating that from where they intersect at -1, sorry, up to 2. So doing this then, what we're going to get, so x cubed there, so we're going to have x to the 4 on 4, and it's all negative. X's, I had 2 there and -1, so I have 1 altogether. So plus x squared on 2, and then I had just a single 2 in there, so that's going to be a 2x. And we want to plug in those values that we have of 2 and -1. Plug in the 2, gives me a -4 for the first bit, plus a 2, plus a 4. And then when we put in that -1, it's going to, negatives won't matter here at all, so that is -1/4. And it's also going to be +0.5 and plus a 2. To the light, we have a negative, so it's not going to be +2, but -2. And from here then, just want to add these all up. What do we get? 4 minus 4 is 0. We've got 2 over there. Another 2 there is 4. Let's do it a little bit differently. We've got 2 on the left. Here is going to be, that's 1/4 minus 2, so that's -7 on 4. But we want to do the negative of that, so adding it on. So that should be 15 on 4. Not quite right. What's gone wrong there? I think it's just me plugging in the numbers in. Is this all correct? 2 lots of x minus blah blah blah. Oh, it should be like that, shouldn't it? So that 2 was actually the x's that we had. We had 2 in there. Actually, it should be 3 x's popping out. Or I didn't actually change the number, did I? Yeah, so that should be a 3. So that changes this to be a 6. Yep. Changes this to be a -3. So change those numbers ever so slightly. What do we have now? 4. And in here then we had, again, 1/4 -3, so that's -11. So it's going to be +11 on 4. This should be 16. Yeah, so 16 plus 11 is 27 on 4. Lovely, that all looks good to me. Yeah, looks very good. The little value of A then, I think we had that, didn't we? Yeah, it's down here. It's -1. Lovely. Next one then, what is going on? Let Q denote the quarter disk of point xy such that they're both, well, all positive or 0. and the, okay, so the inside this circle, I see what's going on. On the axis in figure A, sketch the graphs of these things. Well, these are nice and straightforward. Look at this simpler one. Y is equal to minus x plus 1. Very similar thing now, but just the c is going to change. So what we should see from both of these, they connect from like a half to a half. Just nice and straight lines like that. Nice and straightforward. What's the largest value of x plus y? So we need to make sure we're still on Q. These are all tangents. Well, these are all going to, like, we want to find a value on one of these lines. Every point on this purple line here has the same value of x plus y. So if we want to find the largest value of x plus y, we want to be on one of these lines that has the largest value represented with it. Each one, the largest value is like what x coordinate they go through. Same for the y's. So we want the biggest one. You can see here, like as we move, we're basically moving up here. So we want the one that's not here, but just as a tangent to it. If I kind of recolor it, it's orange. So that's one we want to find. And we know then it's going to happen at this point here. Where is that going to be? Well, everything's going like completely diagonal. So this should be not root 2, but like 1 on root 2, 1 on root 2, I think is that point. Because it's like sine 45, cos 45, do you mean? So it's 1 on root 2. 1 on root 2 as our kind of maximum point. So if we do x plus y, add those together, the answer then should be 2 on root 2, the same as root 2 on 2. No, that's not true. What we're doing? Root 2, same as root 2, isn't it? Is that correct? Let me double check. Yep, larger one is root 2. Lovely jubbly. So for part 2 then, on the axis in figure B, sketch these graphs. Okay, so these are the reciprocal graphs, yeah. Thinking about where they're going to go through is like the square root of these points. So if we imagine drawing like a perfect diagonal going up this way, at some point you get like a half, you get 1, etc. So these are going to go through at a half, at 1, and at root 2. So it might be easy actually to draw that line first and just mark on, like, where's that diagonal? There it is. So 1 at a half, 1 at 1, and 1 at root 2, which is kind of up there somewhere. Yep, looks good. So something along these lines. I don't know how accurate you had to be with these. Probably not very accurate. The shape's what they really care about, and like, do you understand the basic premise of what they're on about? That should be fine. Nice then. What's going on next? What's the largest value of x squared plus y squared plus 4xy achieved at these points? So let's have a think about how we can do that one. Similar idea, like we want to find like the largest of these xy's, don't we? Again, how it was going through this kind of positive diagonal, this has got a value of a quarter. This one has a value of 1. This one, value of 2. So we want the one that gets us there. So whatever line is going to come down, hit that point and then go away again. So effectively, we want the xy. Well, we know at that point it was going to be 1 on root 2, 1 on root 2. So altogether they must equal a half, yeah, when you times them together. So that's going to be like the biggest one that we could get possibly there. So largest value of this is going to be 2, and we know the disk itself is all the points where x squared plus y squared are less than and equal to 1. So the biggest they can be is 1. The biggest this thing can be is a half. So we're going to have effectively 1 plus 4 times a half, so 3. Nice. Largest value now, x squared plus y squared minus 6xy. So the other way around, we want to get kind of the smallest thing. Well, the biggest was going that way. The smallest is going this way. So we can do that as well. Oh, one thing I've just realized is slightly wrong. No, ignore me. Yeah, we can do a similar thing where we want to move down this way now instead. So basically, if we could be on one of these lines, that'd be lovely, because x, y, then would be 0. Because we want the largest value of something, but you're taking things away. So effectively, we want the smallest x, y. So nice if one of them was 0. So can we be on this line and still have a maximum here? Yes. If we pick like x is 1, y is 0, everything's fine. So we'll have exactly that. It's going to be 1 minus 0. So just 1 for the answer. And that all looks good to me. Let's circle both of those. Same thing could be if like it's 0, 1 or 1, 0. I mean, same argument there. Anywhere along like these 2 points would be the smallest value it can be. Sorry, biggest value that I think would be biggest value. That looks good. The smallest value would be the origin. It's just 0, isn't it? Yeah, because you can never make, considering we only have like positive x and y's or non-negative x and y's. So now then, what do we have? Some circle-looking thing. Describe the curve. Describe the curve. Some circle-looking thing in it. Let's split that up then. So x minus 2 all squared plus a y minus 1 all squared is equal to k. And then we would have had a minus 4 minus 1, so plus a 5 over there. So what is it? It's a circle. The center is at point 2, 1, and its radius is the square root of that stuff on the right, k plus 5. That looks good. Move that over ever so slightly. Nice. Yeah, it's a bit bigger than minus 5. That kind of tells you what's going on, doesn't it? So they're not allowing 0 radius as a circle. So we could always one I do wonder about, like, which one are you allowing? Are you allowing a 0 centered, like a radius of size 0? Is that still a circle or not? Generally, like a circle is all the points, the set of points away from a certain distance, like a certain distance away from another fixed point. So if you just set that distance to be 0, there is still 1 point. Is that still a circle? Who knows? I think it's kind of like definition-wise, like what you decide it to be. On this then, what's the smallest value of this circle that we can get? But like, this isn't the circle. This is going to be the disk that grows around that center of the circle, around the point 2, 1. So this should be all okay. Where would that circle be? 2, 1. So it's over here somewhere. Let me put it on here. Over there somewhere. We also don't know how big it is. That can be just determined later on. But you can see we want to eventually hit that because we still want to be on Q. So we want to be the smallest value of this. So what does this represent? It's going to be the square of the distance away from the center of that circle. So we want the smallest value of this while being on Q. So you can see, like, we want to be as close to this as possible while being in this circle. Like being in this circle, sorry, not the little one. So it's going to be whatever the straight line is that connects those up. So if we do that, let's do it in orange again. Connect those through. Should be this point here, wherever that's going to be. How can we do that? Well, we know this is 2, 1, so it's going to be some scale factor of 2, 1 in it. Smallest value of this thing. Yeah, so we need to think about it's going to be the point 2, 1. That's this point here. Let's just write that on there. It's 2, 1. But we want to stretch it so that the magnitude is only 1. So yeah, 2, 1. I think that'll be around 2, 1, like that. This would have nominal magnitude of 5. Sorry, root 5. So we're going to divide it by 1 on root 5. It's not very neatly written. Lovely. So now then, yeah, we have basically 2 over root 5 and 1 over root 5 as our point. Let's plug that all in. What's that going to give us? Well, 4 over 5 plus 1 over 5. That's going to be the 1 that we already knew about. Minus 4 the x's, so 8 on root 5. And minus 2 of the y's, so minus 2 on root 5. So 4/5, 1/5 is a 1. Take away 10 on root 5. That's the same as 1 take away 2. This would be like, if you take a 2 out, you've got 5 on root 5, yeah? That's the same as root 5. So it should be 1 minus 2 root 5, is it? 1 minus 2 root 5. Lovely. Jobly. Excuse me. On to the next one then. Yeah, now we get to the computer side and stuff, don't we? So an n by n grid consists of squares arranged in n rows, n columns. For example, a chessboard, an 8 by 8 grid. Yep. Let's call a semigrid of size n the lower left part of an n by n grid. That is a squares located on or below the grid's diagonal. So we do include these ones. Yep, this is size 4, 4 across this way, 4 across that way. Let's suppose that a robot is located in the lower left corner of the grid. The robot can only move up or right. And its goal is to reach one of the goal squares, which are all located in the semigrid's diagonal. So all of these kind of shaded in ones. In the example shown in figure C, the robot is initially located in the square denoted with R, and the goal squares are shown in grey, blah, blah, blah. Let's call a solution a sequence of the robot's moves that leads the robot from the initial location to some goal square. Okay, How can we get from there to one of these while only moving right and up? So write down all 8 solutions for the size of grid, for the one we can see up there. Okay, this, you can almost think of this as a tree diagram. Do you know what I mean? What ways can we get to one of these grey ones? We can go straight up. I can turn off here. I could turn off there and go that way. I would actually put arrows in, do you know what I mean? Well, there's only one we can go in it. We could have turned off there and then gone straight across. We can, instead of going up, the whole thing now can actually be flipped over, effectively. If I do it with orange instead. We can go straight across. We could go across and then up. We could go across, up, across, and across, up, up. So they're all the 4 possible ways in each way, and then it's going to be just like this symmetrical stuff to get us 8. So what do we have? Up, up, up. It's going to be up, up, right, up, right, up, up, right, right, and then right, up, right, up, right, 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 up, right, right, right. And you can see it's just the all possibilities. Once we've done 3 steps, because we can only move right and up, where are you going to go? Where else can you end up apart from here? Answer, nowhere. So as long as you do 3 steps, you will end up in one of these goal things. That's good. Devise a excuse me. Devise a concise way of representing the possible journeys of the robot in a semigrid of size n. In notation, which of the journeys are solutions? A concise way of representing the possible journeys of the robot in a semigrid. Okay, I think it's just like the way I've written this down. The concise way. So if we say like r equals right, up equals up, u equals up, or like move right, move up. Let's be precise. Move right, move up. Representing the possible journeys. Okay, so now we're just going to have then like I'm trying to think of the way to explain it. We can then represent one journey. So a journey is the same as like a sequence of R's and ups. Sequence of R's and U's. That's good. Which ones are solutions? It's a solution if the length is n. So what are we saying by that? We're going to denote all the ways that we can possibly move by just using up for, well, U for up, R for right. How do we write down a journey? We just list them like this. So I do 3 ups. I do 1 right, 2 ups. How do you know if it's a solution? In this case, you just get to the end. There's no other ways you can get there. Like nothing else you can do. All you can do is move right and up. So if you do 3 steps, you will get there. This is called the Manhattan distance. Think about New York, and it's like the grid structure. All of these squares are a Manhattan distance of 3 away from our starting square. So we're unable to do anything apart from get there because we can only move right and up. If you had lefts and downs, you could just keep going around here forever. Do you know what I mean? Hence why they've not given them to you. So we will eventually end up there at some point. So this shouldn't be n, it should be n minus 1, shouldn't it? Because like we already start at square 1 in a way. So like you're counting from 1, so it's like we're already in some place. Is that fine? Let's see what they say in the mark scheme. Yeah, right R for a right move, U for an up move. A solution in a semigrid of size n is then a sequence of n minus 1 letters, U or R. Yep, lovely, that's good. So part 3 then. Write down a formula for the number of possible solutions in a semigrid of size n. Explain why your formula is correct. Well, it's just all the different ways we can order this, isn't it? So it should be 2 to the power of n minus 1. Because like I said about, I think what I just explained should be fine. What I was saying about the Manhattan distance, do you know what I mean? We can only move right and up, so we are always lowering our Manhattan distance towards the answer solution. So we will get there all the time. It's always going to be 3 steps, always n minus 1 of the size of grid you're talking about. So it should be that we then have like every u and every step that we take, we have 2 choices. Hence the 2. How many steps do we take? N minus 1 of them. So the same as doing here, 2 times 2 times 2, blah, 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 times 2. How many of those things did we have? N minus 1 of them all together. Do I choose up or right, up or right, up or right? And then how many choices do I make? That looks good. So now then, let's change the problem slightly and redefine a goal square as any square that can be described as follows. The lower left square is not a goal square. Okay, so we're always starting, we're not in the goal. Each square that is located immediately above or immediately to the right of a non-goal square is a goal square. So if we start there, these ones up and right must be goal squares. And then each square that is located immediately above or immediately to the right of a goal square is a non-goal square. Okay, so we'd have like no, yes, yes, and then everything above that, so no, no, everything to the right as well, no. So it's going to keep alternating, where we have kind of diagonal sequences of yeses and nos as they go through. So furthermore, let's assume that upon reaching a goal square, the robot may decide to stop or to continue moving, provided there are no more allowed moves. With these modifications in place, write down all the solutions in a semigrid of size 4 and all the solutions in a semigrid of size 5. So of size 4, that's what we already had, yeah? But we will have introduced new goal squares here. So not only will we have the 8 original, but we'll also have the 2 new possible solutions of just taking a step to the right and taking a step up as well. So write down all the solutions in a semigrid. Yeah, so it's all from 4. So it's all from 4 plus up plus right. And then for number 5, think what it said about where the goal squares go. Because all of these are goals, all the ones above it are not goals. And these ones as well. To the right of it as well is not a goal. So when we add in the next diagonal, i.e. making it like a 5x5 semigrid or whatever they called it, we don't add in any more goal squares. They're all non-goal squares. So the possible solutions do not change because we have other positions we can get to that we can then never solve it from. So at no point would you ever actually leave past this, because as soon as you take a step up there, well, you've just lost, haven't you? Same if you go on this one, or this one, or this one, or this one. Because these are always going to be the final step. You can't step up or right from these. So you've just lost. You will always end up stopping at this step. So adding in that next row doesn't change anything. So this is for 4 and 5. Now then, that's good. Looking at part 5 then at the end. How many solutions are there now in a semigrid of size n, where n is a positive integer? You may also consider separately the cases where n is even or odd. So we're always going to, let's do the evens first, because that's probably the easiest way to think about it. But what happened what happened with the 4? Well, we got all the solutions for 4 and these 2. What are these 2? Well, if I get rid of all this rest of this grid, these would be goal squares. So it's just the same as having like a 2x2 semigrid, and it's the solutions to that. So the solutions of if we want to have a number, say 2 times k, some even number, is equal to the solutions of all of them from there. So think about like the original one we looked at, we'd have 2 to the power of n minus 1. We want to have that for all of the possible k's that we're going to have, all the possible 2k's. So it should be the sum as k goes from 1 up to some random number n. And what we're going to have then is 2 to the power of 2k minus 1. We're going to add all of those things up. That should be the solution. Let's go through and make sure this is all okay. So how do we actually do this then? Well, what numbers do we get from that? K is going to change. We can take out a half from the minus 1 at the top. So it's 2 to the 2k. And this is just going to be the same as 4 to the k, yeah? And this then is just a geometric sequence where the first term is 4. We could have had that, I suppose, over here, couldn't we? I've done some steps we didn't need to do. First term is 4, common ratio is 4 as well. So it's going to be a half of r to the n, so 4 to the n minus 1 over 4 minus 1, which is 3. So does that look good? I think so. I don't know why it's a quarter at the front now. So we should have 4n minus 1 over 6. Is that good? Oh, sorry. I need an a at the top as well, don't I? I need an a. So I should have had the 4 as well there. So that makes that 2 over 3, not 6. Apart from that, though, everything else looks good to me. That is it for an even number. If what we're going to do is do like 2, if it's even, yeah, if it's odd, then you're going to have like 2k plus 1. All we're going to do then is think about, let's actually round down first. I'm trying to think of a way to phrase it. If we had, let's just have a little bit of a mess around. We have 2k and 2k plus 1. And we want to somehow map these to the same number. You can obviously think about this like take away a 1 if it's odd. That would be fine. But if we can write it down with like a floor function, it's nice. So if we double everything, we'll have 4k and 4k plus 2. Does that help us? Probably not. No. It might be just easier to write down in words. Do you know what I mean? Okay, if it's odd, take 1 and do above. And just take 1 and do above. So yeah, that should be fine. Basically, if it's an odd number, you just look at, like, say it's 5, you do 4. If it's 17, you do 16. Take away 1, find the even number there. Do that one instead. Because adding in that next row doesn't change any of the answers. Yeah, didn't change anything at all. That all looks good to me. What number was that? 5. 2 more to go. Oh yeah, the liars. So what have we got now? Alice, Bob, Charlie, Diane playing together. When one of them breaks a precious vase, they all know who broke the vase. When questioned, they make the following statements. So Alice says it was Bob. Bob says it's Diane. Charlie just says it wasn't him. And Diane says, calling Bob out, mate. Go on, Diane. So each statement is either true or false. Yep. Explain why at least one of the 4 must be lying. Well, these are mutually exclusive. Yeah, it can't be Bob and be Diane because it was just one of them breaks the precious vase. So Alice and Bob are mutually exclusive. They cannot both be true together. A and B are mutually exclusive. I think you can do a few other things as well, like Bob. Diane's just calling Bob out. Do you know what I mean? So Diane and Bob cannot both be telling the truth as well. So explain why at least one of them must be telling the truth. Let's think about doing like a proof that they're not doing. Imagine they are all lying. Could they all be lying? Is what we're trying to say. Like, yeah, at least one of them must be telling the truth. Can they all lie? So if they're all lying, it's not Bob. Let's think about who it could be. Alice, Bob, Charlie, Diane. It wouldn't be Bob. It wouldn't be Diane. It's not Charlie. No, he would be lying. So actually, it would be Charlie, and Bob is wrong. I think it might be this then. Actually, Diane and Alice, isn't it? No, sorry, Diane and Bob. So he says it's. Can they both be lying? No, it was Diane, so it's not Diane. Might not be the easiest way of thinking about that. Let's think about a different way of doing it. Yeah, let's rephrase that one. Can they all be lying? How can we say they're all lying? Oh. Yeah, if it was Bob, it wasn't Bob. Can they both lie? Because, yeah, what Bob said is wrong. So Diane is just saying that Bob is lying. Yeah, okay. So Bob makes some statement B. Diane makes a statement B. They're just the opposite. They are mutually exclusive again. So Diane and Bob cannot both be lying to each other. Let's think about it. If Bob was lying, it was Diane. So right now it's not Diane. So let's think that way around. If Bob tells the truth. So Bob lying tells us that it's not Diane. And now then, what Bob says is wrong. So if Diana lies, then what Bob says is true. So that tells us that it is Diane. But they're obviously a contradiction to each other. So yeah, we have that Bob, not Bob, and not Diane implies a contradiction. So therefore, they both we can't have them both lying. At least one of them must tell the truth. Therefore, B union D is what we want. So either one of them must tell the truth. That's good. So let us suppose that exactly one of the 4 is lying. So the other 3 are telling the truth. Who is lying? Let me move this out of the way a little bit. Put it up there. So yeah, suppose exactly one of the 4 is lying. So they're all telling the truth apart from 1. So let's have a look. Say it's Alice that's lying. So if Bob is, if Bob tells the truth, then that's going to be Diana. Charlie tells the truth. Sorry, Diane. It's not me. So that could still be anyone apart from him. And Diane telling the truth then tells us that what Bob says is wrong. So that tells us it's not Diane. So again, that's not possible. Yeah. So it can't be that Alice is lying. We can work through. I think we can use the fact that we did above, like Diane and Bob are both can't be happening. Yeah, they both can't be lying. So one of them must be telling the truth. Exactly, one of the four is lying. Can we have them both be telling the truth, Bob and Diana? It was Diane. What Bob says is wrong. So it's not Diane. So that would be that they both can't tell the truth, can they? So let's have a look at when Bob is lying. So Alice tells the truth. That means that it is Bob. But Charlie tells the truth. So that means it's not Charlie. And Diane tells the truth. That means that what Bob says is wrong. It was Diane, so it's not Diane. So i.e. it's A, B, or C. So in that case, that B is allowed in all of them. So that is a valid outcome. Like if all of these things occur, including if we put in Bob lying, it was Diane, so it wasn't Diane. So it's going to be A, B, or C. So again, B is in all of them. So in this case, if one person is lying, Bob is lying because because Bob broke the vase. So who broke the vase? Bob. And my explanation would be this. Do you know what I mean? I think I would just write that down. It's quite hard to put this into words sometimes, but I think that should be a good explanation if you can see what's going on. Let's again move this to the side. Next one then. Number 4. Let's now suppose exactly one of the 4 is telling the truth. So now 3 of them are lying. Who is telling the truth? Who did break the vase? Explain your answer. So let's have a look. 1 telling the truth. Let's imagine it's Alice telling the truth. So that tells us it is Bob. So Bob's lying. It was Diane, so it's not Diane. So it must be A, B, or C. Charlie's lying. It's not him. So it is him. So this is not possible because we get a contradiction. Alice said it must be Bob. Charlie says it must be Charlie because we have, Bob's lying and Charlie's lying. So that's not a possibility. Let's look at Bob telling the truth then. And Alice and everyone else lying. So Alice tells a lie. It was Bob. No, it wasn't. It must have been either Alice, Charlie, or Diane. Bob's telling the truth. It must be Diane. Charlie, it wasn't me. So it must have been either Alice, Bob, or Diane. What Bob says is wrong. It was Diane. So but she is lying now. So what Bob says is true. It was Diane. And in this case, everything tells us it's Diane. So if one person is telling the truth, Bob tells the truth, and that tells us, I need to think about it as well. So Bob tells the truth, and that tells us that Diane broke it. And it was Bob lies, and Bob breaks it, wasn't he? Yeah, Bob trying to save his own ass. Now, so basically, Bob is the arbiter of truth. If Bob tells the truth, it was Bob. If Bob lies, if Bob lies, it's Bob. If Bob tells the truth, it's Diane. So now then, Bob and Diane are kind of going after each other, aren't they? Let's now suppose that 2 of the statements are true and 2 are false. List the people who might now have broken the vase. Justify your answers. So similar sort of thing. Let's actually move this out the way again. I'm going to shrink it down. Put it at the top. So we've got 2. We've got lots of possibilities then. Let's have a look at. I think there's some that are going to rule each other out straight away, aren't there? We might have seen that we can have A and B are mutually exclusive. So we can't even bother thinking about A and B together. They're just going to rule each other out. So let's think about A and C. So A, C, we'll have not B then and not D. So if Alice is telling the truth, it is Bob. If Bob is lying, it was Diane. No, it wasn't. Charlie is telling the truth. It was not me. So it could be A, B, or D. Diane is telling a lie. What Bob says is wrong, so what Bob says is true. It was Diane. That's not possible. Let's have a look. Let's actually write down the list of things that we're allowed to check. So we can have A and B, A and C, A and D, B and C, B and D, and C and D. A and B was not allowed from part 1. A and C we've just checked there, not possible. So let's now check. We want to have a look at which ones do we want? A and D being true, and B and C being false. So doing that, what do we get? It was Bob. It was Diane. It was not Diane. So it could be A, B, or C. Charlie's lying. It was not me. So it was Charlie. There we have a contradiction already. B and C, so not possible. So we can rule that one out as well. Let's change this again then. So we want B and C telling the truth this time. So just the opposite thing. So A is lying, D is lying, B with the truth, C with the truth. So A lying, it was Bob. It was not Bob, therefore. So it could be A, C, or D. B is telling the truth. It was Diane. C is telling the truth. It was not me. So it's A, B, or D. And Diane is lying. So what Bob says is wrong. It was Diane. Oh no, so hold on. Diane is lying. What Bob says is wrong becomes what Bob says is correct. So therefore it was Diane. Aha, Diane's been rumbled. So if we have that Bob and Charlie tell the truth, it must be Diane. So that's one of the ones that is valid. Let's have a look then if Bob and Diane are telling the truth. So let's get another A, another D. We don't want Alice and Charlie to tell the truth. So if Alice is lying, it was Bob. No, it wasn't. If Bob's telling the truth, it must be Diane. If Charlie's lying, it was not him. It must be him. So that's not possible. And last one then, just to go through and check. C and D. So A and B must be lying. So if it's Alice is lying, it was Bob. No, it wasn't. A, C, D. Bob, it was Diane. No, it wasn't. So it must be A, B, or C. Charlie is telling the truth. It wasn't him. So it must be A, B, or D. What Bob says is wrong. It was Diane, so it's not Diane. So A, B, C. So in this case, we have Alice must be the breaker. The only one that is a possibility in all of them. That implies A. Nice. Is that everything we need? Let us now suppose that two of the statements are true, two are false. I've got a feeling for the next one, hence if we don't know how many of the false statements broke one, then any one of the four could break the vase. Yeah, so we have Bob, Diane, Alice. We haven't got Charlie as like an option for things. So exactly one of the four is lying. What have I missed off? Let's have a look at the answers. This was 6 part 5. Either Bob or Diane is telling the truth. Part 4 was saying, let's double check all the answers actually. Part 1, what have we got? Alice and Bob's statements are contradictory, so one of them must be lying. Alice and Bob, yep, that's good. Part 2, explain why at least one of them must be telling the truth. We have that Bob is lying and Diane is telling the truth, and hence one of them is telling the truth. Yep, so we have that they both can't be lying. Part 3, we have Bob to Bob. Bob is the liar, hence Bob is lying. Bob like the Raz, Bob is the liar. Yep, that's good. Let's actually tick these off maybe. So tick, tick, tick. Part 4, we want Bob tells a lie so that we know that Diane broke it. Ooh. So I got the Bob was lying, but I got the wrong outcome here. This shouldn't go to Diane. This should, go to Charlie. Let's double check that then. Get rid of these bits again. So if Bob lies, Bob is telling the truth, but everyone else lies. So Alice is lying. It was Bob. It's not Bob, therefore. So it's going to either be Alice, Charlie, or Diane. Bob tells the truth. It was Diane. Hey, what? One of the four is telling the truth. The other three are lying. Part 4. Bob and Diane is telling the truth. Hence, Alice and Charlie are lying. We can't have Bob telling the truth. Okay. Let's rephrase this ever so slightly. So what's it saying on here? We know that either Bob or Diane is telling the truth. Okay, yeah, Bob or Diane are telling the truth. So let's think, yeah, I did the one with Bob. Let's break this down again. Let's make sure that this can't work. So if Charlie is lying, it was not him, it is Charlie. Okay, yeah, that's not possible, is it? I don't know how I didn't break that down. Yeah, you can see they contradict. It can't be Bob that's lying. So it should be therefore Diane, because yeah, they both can't be lying, can they? So it wasn't Bob that was telling the truth, it must be Diane. So A, B, C, and D. Well, that's all knots. So Alice is lying. It was Bob. No, it wasn't. Bob's lying. It was Diane. No, it wasn't. Charlie, it was not me. So yes, it was. Diane is lying. No, Diane's telling the truth. So what Bob says is wrong. So it was Diane. No, it wasn't. So in this case, yeah, Charlie is relevant in all of them. So it would be that Diane gives us Charlie. So yeah, slightly different. Well, very different, isn't it? And now we have, yeah, all 4 outcomes. So we can see, yeah, hence show that if we don't know how many of the 4 statements are true, then any one of the 4 could have been broken. So if we have 1 true, 2 true, and 3 true, who could have possibly broken it? Well, if we look at what exactly 1 of the 4 is lying, so 3 are being true, Bob breaks it. If we have 1 of them telling the truth, then it was Charlie. And if we have 2 of them telling the truth, then it's either going to be Alice or Diane. Nice, that's useful. Is that all correct? It's only 1 mark for that last one, yeah. Size above. Include cases where each of the 4 have, yeah, okay, yeah, just listing these out is good. Lovely. Last one then. Alice and Bob, they're back again, have a large bag of coins, which used to play a game called HT2. In this game, Alice and Bob take turns placing 1 coin at a time on the table, each to the right of the previous one. Thus, they build a row of coins that grows to the right. Alice always places the first coin. Each coin is placed heads up or tails up and cannot be flipped or moved once the game has been placed. Once it has been placed. Player loses the game if he or she places a coin that results in 2 adjacent coins having the same pattern of heads and tails as another adjacent pair somewhere in the row. Okay, so let's think about that for a second. Like, we have 4 possibilities: heads, 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 tails, tails, heads, tails, tails. So you can see, like, if we see one of these patterns before, we can't do it. So if I've seen, like, if I see a head is the last thing I've seen, but I've already seen a heads, tails, I cannot put down another tails after that and have it be the same one. It must be different. So there's only going to be a few possible things that we can actually do to actually make this, like, how long this game can last isn't very long, because there's only 4 possibilities. So as you think about having, like, the second one introduces the first possibility, third will be the next one, fourth the next one. So we can only possibly have 5 in this sequence. Like the 6th person, if you play the 6th coin, you will definitely lose the game. So let's read the rest of it. Yeah, we've done that bit. Reading a pattern left to right. For example, Bob has lost the game by reducing a second instance of H-tails. HT, sorry. So yeah, he's gone H, and then Bob put another, so it's HH, and then you can see HT, TT, TH, but then we have another HT, HT. But at this point, like I said, the 6th person, like, Bob has to put something down after Alice has placed the heads. Already, we've had heads and heads tails. So what can Bob put down? Nothing. He only has those 2 options. Both of them result in a loss. So this is in a losing position for Bob. Alice wins here. Do you mean Alice wins just by getting there? Alice has lost his game, producing a second instance of tails, tails. Yep, same idea. You can see you can't put 3 in a row, so it wouldn't work. What's the smallest number of coins that might be placed in a game of heads to HT2, including the final coin that causes a player to lose? So I think the shortest you just do, like, everyone puts down a head, yeah, and then we've lost straight away because we need to have at least 3 of them to have 2 twos. Do we not have those 2 and those 2? Yeah, it should be that. So the shortest is 3. Just for that exact reason, we need to make sure we have 2 possible pairs so that we can actually repeat ourselves. If we have just 2 coins, we don't have 2 of the pairs. 3 coins introduces a second pair possibility, so we do have the ability to lose the game at that point. The largest number, same idea that I just said about, we want to have all the 4 possibilities that we have up here, but we want to make sure that they combine in a way so that they, like, you can stick them together in lots of different ways, I imagine. And you can see here we've got, like, the pairs like this going on,
The next coin then would be the one that loses because they have to repeat one of these 4 pairs. So what do we get? 1, 2, 3, 4, 5, 6. The 6th coin will lose, like I said a second ago. What's the largest number? Including the final coin. So yeah, largest is 3. 6, right? 6. Bill can always win a game of HT2 by adopting a particular strategy. Describe the strategy. So we could probably just go and think about all the different possibilities. Let's actually do that. We can think about like heads and tails. We don't need to think about Alice ever playing tails first. You can always just think about heads first and what happens after that. So let's do that. Do I need more space? Maybe I'll move it if I do. So that's going to be Alice going first, playing a head. What can Bob do after that then? Well, Bob can do 2 things, either do a head or do a tails. Alice after that then, let's not bother writing down the ones where like Alice just loses there. She's not going to do that. Do you know what I mean? So this is not a possibility that we need to consider because we can assume that Alice is smart and she will make a good choice. Like you're not going to play a game and then just think, I want to lose. So like, the first thing you do is resign. That's not, we don't need to consider the person that just resigns all the time. Like that's a stupid thing to consider. So what can Alice do in that situation? They can just put a tail down to keep the game going. At the same point, like we've never seen a tails before, so we have both options available to us. That is good. Now then, what can Bob do? And again, we don't want to be thinking about losing the game, really. Maybe we do actually. Let's put these in there. But what we'll do is we'll circle them when someone's won. So Alice can be orange and Bob can be green. So here, Bob wins because Alice has done stupid things and she's done just heads in a row. That's the quickest way to lose what we had down the page underneath. So Bob's choice is then here. From this tail situation, he has freedom because he's never seen a tails before. So he can do anything he likes. And neither case results in a loss. Here, Bob has seen a head before. So if he does a tail, Alice wins. If he does a head, the game keeps going. Alice was orange, so let's circle that as an orange. And now then, the tails. So again, we've seen the tails already. So in that situation, we want to really pick a head. If we pick a tails, then that means that Alice is going to win. You can see basically that like we have Alice's choice. It can basically like Alice can choose to make Bob win. Bob's choice, he can choose to make Alice win. Next branch is then Alice is doing some stuff. Let's circle her at the top just so I know. And over here then, how many heads have we seen? Well, I've seen heads and I've seen heads tails. So every choice that Alice makes, she loses. So no matter what happens, yeah, Bob wins. So we can effectively just do like a line and then it's just like, okay, Bob wins there. And now that's good. Tails then. What have we seen already? So she can't play another tails or she loses. So she's got to play a heads. I see a tails. She's going to make Bob win. Next choice then is this heads in there. We've already seen a heads tails and we've already seen a heads. So this is a situation where again Alice just loses if she gets there. At this point, we don't need to think about that one. She's already won. She gets there. At this point, we've seen a heads before. We've had a heads tails. So a heads is okay. But a heads tails is not. That results in Bob winning the game. And down here, we don't consider it because Bob's already lost. Alice has won. What's left over then? These couple ones that we've got left over. We've got Bob there. What can he do in this scenario? It's a heads. He's seen a heads. Has he seen a heads tails? He has. Yep. So Bob's just lost. Yeah, this is an Alice victory. And bottom one, have we seen everything? It's a heads there. We've seen a heads tails. We've seen a heads. So yes, this again is an Alice victory. So now then, let's look at our tree diagram. I'm actually going to remove. No, I'm going to move it down slightly just to like not have it be the bits at the top so easy. And it's going to propagate back. So if we have something that only results in like for example here, what's going to happen like when Alice makes this choice? If you kind of think, well, I'm only really ever going to pick like this version because she wants to win the game, yeah. She's not going to voluntarily resign and just let Bob win. So we don't really need to consider like the other ones, but we can almost look back and think, okay, this is a complete like this heads results in Bob winning either way. So this head is effectively a Bob win state. because then whatever Alice does, Bob wins, yeah? He set up a situation where like Alice has just lost. She's backed into a corner and she will lose. So that's what we want to be looking for. Where can we kind of truck back through and see, like, okay, it's only if we're going to make sense for them to pick that direction. So looking here, that's a state of Alice losing. Oh, that's a yellow state. Alice winning, sorry. So that's this as well. Same with this one. And let's look back through from the top then. What about this one? Well, that only comes from Bob winning. So that's a Bob win state. Here, both are possible. But it's Bob to play. So Bob gets to choose. Does Alice win or do I win? So Bob's going to pick himself to win, yeah? And going down a bit more, we have this state. And again, Bob is choosing who he wants to win. Does he want Alice to win or Bob to win? Well, Bob wants Bob to win. So he's going to do that. And then we go back here, and Alice is choosing. Well, this one, either way, Bob wins. And then we can see, like, we want Bob to win. We don't need to bother doing the rest of this. We want Bob to win. So Bob can choose these bits and these bits. So all we need to think about is actually Bob can win. Bob can always win. The game is rigged for Bob. As long as Bob matches what Alice does first of all, and then it doesn't matter what Alice does next. If he either she can play a heads and then she's lost straight away, or she plays a tails, and then Bob effectively, if he plays another heads, then he's just given her back everything she's had before. If he picks a tails, sorry, was it? Yeah, this one shouldn't have been. It's a bit weird. Yeah, he's never going to pick that. Do you know what I mean? He's never going to pick there because then Alice will be the other one. So that should be an orange one, I think, because Alice will end up. Bob would just never pick this. Do you know what I mean? Because Alice would win. I think that's all good still. So yeah, Bob just does the opposite. And then either Alice does the same thing and she loses, or she does something different. And then Bob just does the same thing. Sorry, Bob plays the same. So Bob just always basically plays what Alice plays first. That's his tactic, and then he will win. Whatever Alice plays, Bob just continues to play that every single time. Let's check that's correct. Part 2. I think there's more possible ways of doing this, but yeah, that's one of the ways it works. That's good. I think we can go down. Let's do the whole tree for a bit of fun, isn't it? So what's happening here? This is Alice's choice. She gets to choose who wins. But that's the thing. Like, if you get to choose who wins, then you're going to choose yourself to win, yeah. And this is obviously an Alice win state. So yeah, Bob just needs to go down one of these paths. Do you know what I mean? And pick where he's going to go. This again, Alice can choose which way to be at. I think my circles are slightly different than what I'd normally do, but that seems to be fine. Like, as long as Bob does this, it's going to go heads, and then yeah, Alice plays a head. Bob goes, okay, I'll play heads too. And then obviously Alice can either then play a heads and it's lost, or she plays a tails. So we're following this path now, and then it's like, okay, what's Bob going to do? He's just going to play a heads, and then there's nothing that she can do. Yeah, so he matches the first, negates the second. Because either he matches the first and then she just loses, or he matches the first, she does something different. So he just keeps playing whatever she first plays until he wins. That looks good. For any positive integer n, there's a game called HTN with the same rules as HT2, except that the game is lost by a player who creates an unbroken sequence of n heads and tails that appear elsewhere in the row. For example, Bob has lost this game of HT3 by producing a second instance of tails, heads, tails. Tails, heads, tails, tails, heads, tails. Suppose n is odd, and Bob chooses to play by always duplicating Alice's previous play. Alice knows that this is Bob's strategy, so that Alice can always win. Okay, let's go on to a new page maybe. So n is odd, so we're playing HTN. N is odd. And they also told us Bob chooses to play by always duplicating Alice's previous play. So Bob is a copycat. So let's think about a situation. Does Alice always go first? I think Alice always goes first. They've always had Alice going first, yeah. Alice always goes first. So Alice has a choice of either doing heads or tails, but again, the choice is arbitrary. It's called without loss of generality. Like, it doesn't make a difference. Our graphs would be exactly the same if we just swapped it over from like heads becomes tails, tails becomes heads. Nothing would change. I mean, you just get the exact same graph with a tails and everything being the inverse of itself. So this is Alice's first choice. She picks a heads. Bob then also has to pick a heads, doesn't he? So the game just always starts like that, and then it's back to Alice. Let's do my circling again. That's that one, that's that one, and that's that one. So after this then, Alice has a choice. She can either play a heads or a tails. And then Bob has a choice. If he plays a heads, he loses. So what they're doing that's an Alice win condition, isn't it? This is a Bob. And if he plays a tails, what happens? Not much. That's just going to keep going. Underneath then, he could have played again heads or tails. Both things are fine. We don't need to consider that one because that one's all done. So tails then, he can again, or she now, can play a heads or a tails. Anything we've seen there that's scary? I don't think so. Heads, 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 tails, heads, tails, heads, heads, tails, tails. It's going to be very hard to track exactly which bits we've got. I'm wondering if like it's going to be as simple as just like do 5 in a row. Yeah, if she just keeps playing. Okay, yeah, overcomplicating this. Look at the answer very quickly. You could do this and then figure it out. It's going to take you a long while to do. But effectively, because he's copycatting, if she plays heads, heads, if she just keeps going up, do you know what I mean? You can, yeah, this is the easiest way. She gets to choose. So what am I doing? This is an Alice win state. So Alice gets to choose, do I want to win from this point? So yeah, she can. And Bob doesn't have a choice there, does he? He has to play this. Bob gets no choices. So Bob is always doing that. This is just, yeah, okay, easy. Alice is just going to continually play the same thing, whatever it is, and then she wins. So if Alice is just boring, Alice plays, always play head. Or tails, do you mean? Just do the same. Always play the same. That's good. Last one up in here then, was it? In these games, a maximum time of 1 minute is added for each turn. Can we be certain that a game of HT6 will be finished within 2 hours? Whoa. 1 minute. Okay, so we've got 120 turns. I don't know why they bother doing that one little step of like, just can you do it in 120 steps? That just rephrase it. Are you guaranteed to win in 120 turns? Can the game last 121 turns? So that was HT6. How many possible arrangements are there then? There's going to be 2 to the power 6. That's 64 possible arrangements. What we saw above, we had 4 like this, yeah? Because you want to be able to make sure that you don't overlap them. Trying to think of a nice way to explain it. Yeah, they can't be overlapped at all. This seems like it should, like, this is more than 60. And then I think we're going to be able to get like 2 versions of it maybe. Because there's going to be 6 possible ways. Like when we do the next one, we're going to lose. But they do overlap. But you got to think about the fact that, like, okay, yeah, because there's this many of them. But it's not just going to be that many many letters in the sequence. Every single one, half of them will have tails at the end, half will have heads at the end, and the same for the start. So it's almost like you need dominoes. You know dominoes, and you have like, I have a 1 and a 5, and I put that down. Then I could put a 5 and a 4, and I put that down. Then I could put a 4 and a 2, then I put 2 and a 6. And you have to always link the one from before. So there's going to be some chain of them connecting together. Like, can we always guarantee, like where I had this earlier, that you can go in one big circle all the way round? Like we've gone through all 4 possibilities without it having that like we had the same thing. Does that make sense? Like at no point did we get a repetition just prematurely. But what happened was that we had to lose one. Basically, the last one of them is the same as the first next one. So even though it said a sequence of 2, really it's like we have a sequence of 1 for each one, and then just plus 1 on the end. So it's going to be a very similar thing now. We have 64, 6 sequences, like 6 things long sequences, but there's going to be 1 overlap. So effectively we're going to have 64, 64 times 5, so 320, I'm guessing, is like the maximum length of the sequence that we can play. I think as an upper bound, whether that's possible to actually make that domino sequence to get it all to work, but I think we can play this 320 and then that this person lost. No, they haven't lost yet. 1, 2, 3, 4, 5. They haven't lost yet. So it's going to be that plus. So this takes us all of these bits. We want to then also have. Does it get more complicated than that? I'm trying to think if this is a good upper bound, or if we can get much, much, much lower than that. 64 different sequences that are possible. Each of them is 6 long. We do need an overlap to kind of join the sequences together. So it's like they're 5 long. That gives us then 320 in that row. That's more than 120. It's way more than 120. What are they saying in the mark scheme? In a non-losing sequence, some n element sequence will begin at position 1. A different one will begin because I see the one bit I've missed up. Then we don't clip on the end. That's the way to think about it. Okay, slightly phrasing this. It's not going to be 1 overlap. It's 5 overlap. So effectively, then what we're going to have is it's not correct, because you can have like heads, 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 heads as the first one, and duplicate, and then you can see that this one we can change it not to do the same thing but just tails. And then if we duplicate this again, we'll duplicate these bits, and then you just need to make sure that like the bit on the end is different than what you've had before. I think you can just keep swapping through, and this comes down. But either way, you can see that like how long is this thing going to be? Well, we start with a length of 6, and then every one that we add, we actually just add 1. So we're going to have 6 plus 63 is equal to 69. Plus then the 1 on the end as well. 6. Yeah, and then plus the 1 to lose. So 70. Let's just clarify all of these bits. So, yeah, the 70th is the losing. Coin. Yeah, so HD6. So we're looking for sequences that are 6 long. When we have this, it's like we don't think we have to have then the next thing you put down, you make a new 6 sequence, and the next one you make a new one. So the overlap is not 1, it was 5. So all of these ones get repeated in the next one, and then you just have a different thing at the end, or something happens at the end. So how many possible ones could we get? Well, there's 64 different sequences available to us because we have a length of 6. So we had the one that we started with. Every other sequence then adds on a length of 1 to our entire game. There are 63 other sequences. So we start with a 6, we add on 63s, lots of 1, and then that gives us the entire possible sequence of things that we can get. But we haven't lost yet. We have to put down the 70th coin to lose the game. So in that case, 70 is less than 120. So therefore, what do we want to find? We're certain that we will be finished, yeah, certain. Is that good? Let's just double check the answers in here. So in a non-losing sequence, some n element sequence will begin at position 1, a different one will begin at position 2, and so on. There are 2 to the n distinct sequences of length n, thus no new n element sequence could begin beyond 2 to the n. If the final distinct sequence begins at 2 to the n, it can end at 2 to the n plus n, and any element that follows it must lose the game. Therefore, no game of HTN can involve more than 2 to the n plus n moves, including the losing move. This question asks whether 120 is... Yeah, so this is good, because this was 2 to the n. Yeah, because what we've got is 64. 2 to the n plus n. 2 to the 6 plus 6 is 70. So yeah, we are the same thing. Different logic to get there, but same sort of ideas. Is that the end of it? Okay. I think though. Yep, lovely. Hopefully that was very useful. Any questions let me know in the comments and stuff. Yeah, thank you very much for watching. Good luck when you do the real, I'm guessing ESAT or something like that or TMUA in the autumn. So thank you very much for watching. See you later.